Welcome back to our Future of Quantum Computing with Jack Hidary, one of the most brilliant thinkers in this area from Alphabet X, formerly known as Google X. And Jack, I'm so proud you're a member of the X Prize Board of Trustees as well.
Peter, it's been great to be associated with and active in the X Prize for these number of years. What attracted me to X Prize in the first place, when you and I, let's not date ourselves, let's not mention how many years, let's not mention it, okay?
Fine,
but what I think what is so attractive about this model is that it allows us to not select the technology, but point a huge spotlight on the problem and say and invite the world, entrepreneurs, innovators, inventors. They could be experienced engineers, or, as you and I know happened in many, many cases, high school students, right?
Incredible.
Competing in these kinds of competitions.
But we digress.
Oh, yes, sorry.
Let's jump in. So welcome back to module number 3. We're going to go into the details of quantum computing. I'm going to split this into two parts, part 1 and part 2. And what I love is the way you make it understandable. So let's jump in.
Yeah, quantum computing is intense, Peter. And
it is.
I recommend to the viewer at home to take a break, get some snacks between part 1 and part 2, because they'll need that sustenance.
And that's your brain working.
Exactly.
And by the way, one of the things people talk about is the brain actually a quantum computing device?
Well, it's a fascinating question.
But not right now.
Which is part 7 of our series, okay? But I was actually only half kidding, joking with my publisher of the book, saying, I think we should include in every book, we should wrap around some dark chocolate, 90%, cacao chocolate, because that's the kind of intensity that this book needs, from our brains. So maybe that'll be a future version.
Got it.
Okay, let's talk about quantum computing. What are the kinds of problems we can solve with quantum computers? How do these things work? What are these things? What are these quantum computers? And so, brief history, we're not going to read off everything on this, but let's just kind of set the stage. Richard Feynman is often a name that comes up when people think about the history and the origin of quantum computers.
One of the coolest scientists ever.
Absolutely. And he had a lot to say about a lot of things, including being one of really the fathers of nanotechnology, where he said there's a lot of room at the bottom. What he meant by that is that there's a lot of room to potentially make innovations at the smallest scale of things, this nanoscale, right? And so you look at Feynman's quote, he said, nature is not classical, damn it. And I want to highlight the damn it as well.
Because it would have been easy if it was.
Yeah, exactly. So when he says nature is not classical, what he's talking about is that if it were classical, if it were not quantum, then we could just, if it was basically like billiard balls, like Newton said, right? You hit one billiard ball, it hits another, and so on and so forth. We could use a classical computer, and then we could model.
Predictive.
Right. Predict and model. If we know the entire state of a system at time 1, we can then predict it at time 2 just by moving forward all those equations that
ad infinitum.
Exactly, that Newton gave us. But in fact, our world is not that way. As we discussed in the first part, in section 1, part 1 of our video series here, the world is quantum in nature. And even though in our macro sense, we don't see these quantum phenomenon every day, all of us are made of atoms and subatomic particles that are quantum. And so while these effects do get washed out a bit in the macro scale, that's what we're made of. We're made of quantum mechanical stuff. And so because of that, if you wanted to understand the universe itself, nature itself, Peter, you'd have to have something that is beyond just a classical computer. You would need a computer based on quantum mechanics itself. Now, I do want to give credit. It's true, Richard Feynman did say this in 1980 in a speech. He wrote it up in 1981, which is this paper that we're referring to here. But before he did that, Paul Benioff, no relation to Mark Benioff, I checked, did write a paper in 1979 that actually laid out all the key elements of a quantum computer. And often he's looked over. And often that happens, as you know, in the history of science and technology, where there's one initial innovator, but maybe somebody more famous came along. And so while Richard Feynman deserves a lot of credit, because using his base and bully pulpit at that time as a Nobel Prize winner to then let the world know that quantum mechanical computing would be very interesting, Paul Benioff really deserves the credit for one of the first instantiations and understandings of a quantum computing device. So I do want to highlight that and put that in the record here today.
Okay.
But when we think about other really key timelines in terms of the milestones of this particular history, Seth Lloyd deserves a lot of credit for writing a paper that really helped the field realize that not only was this theoretically a cool idea that Paul and Richard Feynman came up with, but also we can actually build such a device. And this paper we're referring to right here in 1993 was really one of the first to state in some detail how you would actually use a quantum mechanical system, phenomenon to actually do computation.
Because there are lots of different kinds of qubits right now, ways
correct.
that qubits can be expressed or stored.
That is correct. Anything that is quantum mechanical could, in theory, Peter, be used as a computation device. Now, one interesting question that we're not going to answer today, but I want to leave the audience with and just plant a seed.
You got that? This is for you.
This is for you, okay? Which is, we had quantum mechanics and quantum physics from Einstein, from Schrödinger, from Heisenberg, from Bohr, all these greats who helped us get quantum mechanics. By 1930, we had it pretty locked down. We kind of knew the theory, the mechanics of it, even the equations.
We knew the math of it.
Right, we had all that. But then it took 50 years from 1930 to 1980 for someone to realize, Paul Benioff, Richard Feynman, and others to realize, you can use this to do computing. Why? Why did it take 50 years? And you and I have studied very carefully, both of us, Peter, this history of innovation, why something might go unknown and unseen for years, maybe centuries sometimes, until someone says, hey, let's go ahead and do that thing. It could be longitude, right? It could be space flight in some other ways and things like that. And so I'm not going to answer that question today, but maybe at a later time we can converse about why the 50 years when the smartest human minds in the world at that time, John von Neumann, all these folks who knew both computing and quantum mechanics.
Or just focused on classical only.
Right. What happened? What happened there? So we'll come back to that maybe another day, but let's come back to Seth Lloyd, who's currently at MIT, and his realization that you can actually build these things. And we're going to discuss today some of the different quantum mechanical systems, be it trapped ions or photons or other kinds of systems, right, that can actually be computing devices. So what is a quantum computer? I want to give a shout out here to David DiVincenzo. David DiVincenzo, back in 1996 and then in the subsequent paper in 2000, spelled out 5 criteria for saying, is that thing that is puted to be a quantum mechanical computing device, is it truly that one? We're not going to go into a lot of detail here, but I want to kind of, if people are interested, they could check out David DiVincenzo's papers and articles and understand what does it really mean. And so I'll just highlight some of them here today. Do you have qubits that you can initialize the state of? That is, we talked about how a qubit could be in a 0 state, a 1 state, or it could be some superposition of those states. Do I have the ability, as the operator of this quantum mechanical computer, to initialize it in the state at my will? Can I say, oh, Peter, you want to do a certain computation? Well, to do that, I need 50 qubits, and those 50 qubits should start in state 0. Do I have the ability to initialize them in that state? Another one is that we have to make sure we can address each one of those qubits singly and uniquely. That is, we can say, qubit number 2, attention, you now need to move to state 1. Qubit number 17, you need to move to some superposition of 2 states, right? And so the ability to address and understand how each qubit is going. And then also, number 3, the system's qubits must be able to hold their state. What does that mean? That means that if we put it in that state 0, we can initialize it as per number 2. Can it hold that state 0 and for some period of time?
Forever, or do you
not
define
forever,
it?
but some period of time such that we can then do useful computation.
Got it.
And so that's what we mean by that second thing there. And there's 2 more criteria that David put out, and the ability to apply certain kinds of operators. Let's call them gates or operators. These are our ability to modify the state. We're going to look at some examples.
Classical
Peter.
were the and, nan, nor, or state.
That's correct. And we're about to look at some quantum versions of these operators. And we have to make sure that at the very end, we can take a measurement of this system.
We need to output it.
Right. We need to have some kind of output. We need to measure the system so there's some kind of output. And here's one interesting thing about quantum computers, Peter. The output of a quantum computer is classical information. Sounds weird, but true. Okay. So let's talk now about one of the first moments in time. So now I've given you a bit of the history that in 1979, 1980, we had Paul Benioff, we had Richard Feynman conceiving that this idea of quantum mechanics, this superposition, entanglement, the stuff of Schrödinger and Einstein, and could be used to compute. And then in 1993, Seth Lloyd and others, ultimately after that, realized you can build one of these things. And now in 1994, just a year later, Peter Shor, working in Murray Hill, New Jersey, in Bell Labs, looks at previous work done by Umesh Vazirani, by Ethan Bernstein, by Daniel Simon, by others in the field, and puts it all together, and in a stroke of genius says, I can build an algorithm on a quantum computer that can crack the kind of cryptography that we talked about earlier in another part. That is RSA, or public key cryptography. And what he realized in his stroke of absolute insight is he can put different pieces together, including a new piece that he added, to allow a quantum computer to do that in seconds to minutes. Exponentially faster, as we can see in this chart here, compared to a classical computer. So in a classical computer, if you had the largest supercomputers in the world, it might take you hundreds of thousands to billions and billions of years to crack one long key that's used in RSA, depending on the length of that key. But what Shor showed that in literally seconds to minutes, we can crack that same key on a quantum computer. So this is truly exponential. Sometimes people use exponential in a very metaphorical sense. We're using it here in a very literal sense.
Yeah.
This is truly an exponential speedup. Now, when that paper came out, it was a reverberation and a ripple across the entire scientific field, because we then knew, everyone knew, that one day, if ever anyone built one of these things, it would have powerful implications. Certainly for communications.
Geopolitical implications.
Exactly. But once you discover one opening, probably it's the case that you could do other kinds of things exponentially as well, or certainly faster. And so it really started to strike the interest of many in this particular field. So Peter Shor deserves a tremendous amount of credit for having opened the door to a realization that one day these quantum computers would have profound, profound implications for our world. We already talked about superposition. I just wanted to have this here to remind ourselves that, again, from a previous module, if people have a chance to go back to that module and refer back to the idea that in quantum mechanics, Peter, you can have something like in a classical situation, if this is an electron, it can be up or down, but it can also be in a superposition of up and down. Some indeterminate state, Peter.
And by the way, does the superpositioning come in quanta itself, or is it just a mixed, not determined state?
Let's call it an indeterminate state, and actually, it's a continuum, actually. So that actually could be 99% of the zero state, 1% of the one state. It could be 80% of the zero state, and any number in between. In fact, those numbers are not even just real numbers. That is, they could be 0.000, something like that. They're actually complex numbers, and therefore, they can be a true continuum of numbers. In fact, we represent it by this ball, this sphere that we have here on the right side. And so in the classical world, we have the idea of the bit. As we mentioned in an earlier module, 0 or 1. If the capacitor is on or off, we say if it has a charge or doesn't have a charge, it's in a state 0 or it's in a state 1. That's the left side of this particular chart here. On the right side, we see the nature of a qubit, of a quantum bit. Let's shorten that to the word qubit, Q-U-B-I-T, qubit. And in fact, what we see is that when that arrow is pointed up, it will be, say, representing the state 0. And when that arrow is pointing down, it's representing the state 1. But, as you can see, it's a sphere. Well, if it's a sphere, that means that we can manipulate that arrow to be ending on any point in that sphere. Thus, there is an infinite number of possible states of my one qubit. Just my one qubit has an infinite possible set of states. So that is what we call on the right side a Bloch sphere, B-L-O-C-H, after Felix Bloch of Stanford, who named that and gave us this kind of framework to understand it. But you can just see very clearly here that 0, 1, that's only two possible values, two possible states for my bit, my binary digit, my classical world ballgame. And here I have an infinite number of values. And so let's now talk about the idea of quantum supremacy.
Sure.
You asked about quantum supremacy earlier.
By the way, very cool term. That doesn't mean what you think it means.
Quantum supremacy is a fascinating idea that was coined by John Preskill a number of years ago, John Preskill of Caltech. And what he set out and said, if you had a boxing ring and you had a quantum computer in one end, he'd actually use a boxing ring as an analogy, but let's use that today. If you had a boxing ring, and in one corner we have the quantum computer, and in the other corner we had the most powerful classical supercomputer on the planet today, or even in the future. And you ask them to do the same computational task. So it's apples to apples in terms of comparison of these two computational things. And in fact, then you looked at it and you said, how many cycles will it take for the quantum computer to do its thing, and how many cycles will it take the classical computer to do its thing? And sure enough, you compare them. If this is advantageous over that, that is, if it's much shorter to run on the quantum computer, we say that we have supremacy. In point of fact, we even want to look for something that would be exponentially better to run on the quantum computer. Now, the task that you choose, Peter, for doing quantum supremacy testing and benchmarking doesn't have to be a useful task. Doesn't have to be something that cracks RSA or something like that. It can be something more near term, something that we can do today. In fact, that's what the team, and my team had nothing to do with that. Their team deserves all the credit.
So just to be clear, when Jack is talking about his team and their team, this is your team at Alphabet X versus the quantum computing team at Alphabet.
At Google, yeah. That's right. And so their team, ingeniously working on this now for about 10 years, chose a particular algorithm, put it out there for the world to see a number of years ago that this is going to be the algorithm that we're going to use.
It was your lab bench test.
That's right, that's right. And so it was out there, the community understood this was going to be the apples to apples comparison.
It wasn't actually a useful thing.
Not a useful thing at all.
It was a computational
test and demonstration.
Ruler.
That's right, exactly. And sure enough, what now is out in the papers discusses and demonstrates that a quantum computer can do it in a matter of minutes, and a classical computer would take probably 10,000 plus years to do that very same thing. So thus we've achieved quantum supremacy. So you and I are now living in a moment in a post-quantum supremacy world.
As you said, a Sputnik moment.
Yes.
And it's interesting, right? Because we have moments in time when Deep Blue won against Kasparov, and we now have when a quantum supremacy event
was established.
Yeah.
Exactly. So this is an incredible moment. It's a moment akin to 1994 when Peter Shor demonstrated that one day people can run his algorithm. We now know that we can both build a quantum computer that can run these quantum operators that I'm about to discuss now in a few moments. But now we also know that a quantum computer can do some tasks, not all tasks. And I'm going to want to make sure we demystify and take out the mythology of some of the popular press. It's not that quantum computers today or in the future will run all things better. We're not going to use quantum computers to run spreadsheets. We're not going to use quantum computers to do those kinds of things. We are going to use them for certain specific things that they're very good for. So the future of our computing world, Peter, is a hybridized future.
Sure.
It's a future that has classical computers sitting alongside quantum computers. And here's the most exciting thing, I think, about quantum computers in terms of the near term. They're coming to us on the cloud.
Yeah.
So this is one of the things that really differentiates this revolution of technology, Peter, from previous ones. It's going to be cloud native.
I mean, that's incredible, right? Where it doesn't matter where you live and the
You could be in Mumbai, you can be in Dakar. No matter where you are in the world, you're going to have access for free, I believe initially, from all the major cloud providers, for free to this incredible physics-based computational
I mean, it's incredible. We're living in a time right now, and you talk about this a lot, where we're going to see another 4 billion minds coming online in the next half dozen years. And they're coming online, not like you and I came online on AOL, right? 9600 baud. They're coming online with access to, quantum computing on the cloud. That's extraordinary. What will they discover and create?
And how will they use the quantum computer that's available in a hybridized fashion with the classical computers they have also available on the cloud? So here's another way just of looking at this. On the top, we see our classical bits, Peter, 0 or 1 only, black or white. Right. But on the bottom, we have our quantum bits, our qubits, and we see that we can then address all 2 to the n possible states. So you can imagine now, I like to think of it almost like an artist would, that do I have a small canvas to paint on, these little bits? Do I have a large computational canvas, this massive Guernica style, size canvas to paint on? And so that's what a quantum computer is. It's a massive computational space, right? And what we see from the Google papers is that just 55 or so qubits was able to best 2.4 million cores in the classical
It's almost
computer.
Unfathomable.
Right? 55.
Yes.
And not 2.4 million bits. I'm talking about billions and billions of bits housed in 2.4 million cores in the Summit supercomputer in Oak Ridge, right? So look at that kind of comparison. That gives us a sense of the power, the computational vastness of space that we have in the qubit compared to the bit. Just think about that kind of ratio. So we talked about the block sphere, and now let's talk about how we actually move things around the block sphere. So if I had something in state 0, we talked about, Peter, how that is an arrow pointed up on this particular block sphere. It starts at the origin and points up. It ends right at the top at the North Pole of this particular planet-like sphere. And I apply this operator. What do I mean by an operator? What's an operator? Well, you alluded to before that in the classical world, we have a number of operators. We have the AND operator, A-N-D, and what AND does is it takes 2 values, say from 2 different bits that are coming in, and it looks at both of them and says, I'm going to run a test here. If both of them are coming in 1, I'm going to say the answer is going to be 1. Yes, check. If only even one of them comes in at 0, or both of them come in at 0, I'm going to give the answer 0 coming out. So that's, I'm going to the AND gate. You're going to give me 2 bits. You're going to give me, say, let's put up some fingers. Let's put 1 and 1. I'm going to give a 1 as the answer. You're going to give a 0 and 1. I'm going to give a 0 as the answer. 0 and 0. I'm going to give a 0 as the answer. So we've now performed an operation, right? You've given me 2 bits. I've performed my AND operation. That's my job as the AND gate. We can say gate or operator. And also we could represent these as matrices. And I know people might get scared with a little bit of math, but again, that's where the T comes in that we mentioned before.
and the chocolates.
Right, exactly. And so these were the kind of gates that we use in classical world. In fact, it was shown years ago that a certain kind of gate, the not AND gate, right, the inverse of what we just did,
yes.
right? So now let's again, if you give me that, I'm actually going to give a 1 now.
And now?
Right? If you give me 1 and 0, I'm going to give a 1.
And?
Right? Now I'm going to give a 0.
Right.
Okay? So that's a not AND gate. It's
yes.
the inverse
right.
of an AND gate. That NAND gate was shown years ago by the theoreticians that it's universal. What does it mean by universal? It means that from just building it from NAND gates alone, we can build a computer that does any kind of computation. No matter what kind of computation we want to do, be it modeling the weather, be it doing an Excel spreadsheet, any kind of computation we can build from NAND gates. That is the classical world. Now let's turn to the quantum world. We can't use AND gates, we can't use OR gates in the quantum world. Why? Because they're irreversible. Because you showed me a number of different states that I gave the same answer to.
Right, and I had 3 different states that gave you,
a 0, right? In the case of the AND, you gave me 3 different combinations that I said 0.
We couldn't know which one originated. Right.
Exactly. Therefore, we call it irreversible. Looking just at the end point, I can't reverse back out to your particular individual state. And so, irreversible computing is not allowed in the kind of quantum computing we're talking about here today. We have to restrict ourselves, Peter, to reversible gates, reversible computing. So, what is the only classical gate that we can bring forward from the classical world into our quantum future? The NOT gate. Why the NOT gate? Because let's try it again now. I'm going to be a NOT gate, you're going to be my input, and I'm going to show my output with my hand over here.
Right. So please 0 and 0.
Now, with the NOT gate, you just give me 1 value. Just only 1 value. You give me a 1, I give a 0. You give me a 0, I give a 1. We're done. And because it is a 1-to-1 correlation between you're giving me a 0, I give a 1, you give me 1, I give a 0, it is reversible. If I look at the end state, I know exactly where I came from.
Okay.
So we're allowed to take this from our classical past into our quantum future. And so let's now talk about it from the block sphere point of view. If I start now with an arrow pointed up as a 0, and I apply the NOT gate, I will then move it down to the 1 state, right? Okay. And so if I have the 1 state, I'll move it up to the 0 state. And so that is the X operator or the NOT operator. Now we have a slightly more complex operator, the H operator, known as the Hadamard operator. And what happens in this particular case is we're offered either a 0 as an input or a 1 state as an input. And this allows us to put it into superposition of 0 and 1. Now this is the first real breakthrough we're talking about now in terms of quantum computing. We're actually doing a physical thing. This is not modeling quantum physics. This is not referring to quantum physics. This is not a simulation of quantum physics. Peter, this is quantum physics.
Okay.
In the quantum computer itself, we're taking a physical thing, and it started out, say, as a 0 state or a 1 state. Again, the block sphere would be this way or that way.
Yep.
And we're going to turn it sideways, meaning a combination of 0 and 1. Some mixture, right, of 0 and 1. And that's what the Hadamard operator does. When you put a Hadamard operator in a sequence, what we call it a circuit is the way we say a program in quantum computers, and I hit run, in the real world, I have actually taken a physical thing, taken it from a definite state in the basis of that particular computer, and I've now put it into a superposition of states. I physically have done that. And that's the most amazing thing. One of the key takeaways for our audience today, Peter, is that when we do quantum computing, we are doing actual physics. We are not referring to physics the way that classical computers refer to, say, the climate when they're modeling the climate.
Right.
So that is a very big distinction. And then I want to just talk about just one more operator here before we move on, which is the C NOT gate, control NOT gate. Now, again, this is the kind of gate that needs 2 qubit inputs, and I then apply it. What this will do, without going into a lot of details here today, it will entangle these 2 qubits. So I now have a NOT operator. I can go from 0 to 1, 1 to 0. I have a Hadamard operator, a superposition operator that can take something from a definite state of 0 or a definite state of 1 and put it into a superposition. And we talked about that being a foundation of quantum mechanics before. And now here's our other concept from quantum mechanics we started out with in the first module of this series, entanglement itself. I can entangle 2 qubits. Again, I'm not doing it in some simulated way. I am really doing entanglement in the physical computer. And so with these kinds of operators and other operators that we don't have time to go into today, I can build...
Just to hit it, meaning you're using actual physics to represent the state.
That's right.
Right.
That's
you're
right.
actually,
to move
you're
the
actually
state,
entangling. It's not a representation of it. You're
Correct.
actually having to create a
physical thing
that is
truly entangled.
Superpositioned or entangled
That's
in
right.
this case.
That's right. And what we're doing is we're taking that arrow, Peter, and we're moving it around our block sphere. And we're moving it in different ways around, and therefore we're allowed then to represent any one of those states that we can represent on that sphere in our computer. And so what that builds up to is a quantum circuit. And here, let's now figure out how to read these things. We read it like a music score, left to right. We start on the left with those qubits that you see over there, those round purplish circles.
Right.
We'll represent some of them starting out in a state 0, that is up, some starting out in a state 1, that is down. Okay. That's what we call, if you recall, the initialization of our qubits. We initialize them in either a state 0 or state 1. We then apply those interesting operators in the dark purple there called Hadamards. What does they do? They put our definite state into a superposition of states. Those are the Hadamards that you see over there. And then we'll apply a series of other gates that we won't go into today. And finally, we'll end up with the red area where we do the measurement.
We read it out into a classical measurement.
Exactly. And so now here's one of the fundamental differences between classical computing and quantum computing. In the classical world, what we're used to is we're used to taking data from memory. That is, I've got memory stores here of lots and lots of data. They might represent, for example, transactions that happen at our retail store that we're managing. And then we want to bring them into the CPU, and we want to do some calculation on them, right? The ALU specifically, the arithmetic logic unit. We do some calculation on them saying, okay, what if we doubled the number of sales? What would that mean for inventory or something like that? And then we put it back into the storehouse, back into the memory. So we take stuff from memory, put it into the ALU, operate on it, put it back into memory. This is classical computing. In the quantum world, we don't do any of that. There is no memory. There's no hard drive. There's nothing of that. We take our state of qubits, and the analogy I like to use is a potter's wheel. If you and I were potters right now, we'd take a bit of clay, we'd put it on our potter's wheel, we'd start getting it going, we'd shape that clay into the vase itself. We don't take it, bring it, take it, bring it, right? We shape it, Peter, on the wheel.
Yep.
So I call quantum computing of this nature computation in place.
Sure.
Computation in place. It is not shuttling bits around, information around. We actually shape the computation, Peter, is the pattern of qubit values that you see at the beginning being transformed by the application of operators that you see happening from left to right in some sequence. And then the final measurement is a sampling, not of all the qubits. We're not allowed to by quantum computing sample all the qubits, it turns out. We can only sample basically one of the values. And so the quantum computer, and here's the final thought I want to leave our audience with in this module. The quantum computer, Peter, is a probabilistic machine, not a deterministic machine.
That's
and
a
this
big
is
deal.
a profound statement.
Yeah.
If you and I have a classic computer, be it our phones, be it a laptop, be it a supercomputer, if we run the same program again and again and again, we'll always get the same answer because it's an error-corrected, deterministic machine, right?
Data in, data
out. Exactly. Yep. Program will always run the same way. Not so in the quantum world. This is a probabilistic machine.
This is the spooky stuff.
This gets very spooky. But we can leverage this, and we know how to manipulate the probabilities prior to measurement. We know what operators to use so that we can actually get the answer we need out of this. And for another day, we can discuss how we do that. But the good news is, over the years, the field has developed a series of techniques to understand these probabilities and shift these probabilities to such an extent that right at the measurement time, we can measure the state and with high probability, get out the answer that we need.
Amazing.
So, Peter, with that, we can now pause here on this module, and we can move on to the next module as we further understand quantum computing.
Amazing. I hope you've enjoyed this. I'm learning alongside with you because all of this it's evolving right now. This is right
real
here,
time,
right
real
now.
time.
And it's technology and capability that's going to transform the world. If you thought the world was moving fast, hold on to your seatbelts, because as we're going to determine, these quantum computers are helping us understand complex natural systems, material sciences, pharma, the
drug
weather,
development.
drug development, all of these things. It's about to go into hyperspace.
Correct.
Jack, thank you, pal. See you soon on module number 4, part 2 of the quantum computer.